Welcome back to School's Not Out, where we were discussing CSEC mathematics. The last lesson we would have looked at the order of a matrix, and that's defined in terms of the number of rows and columns. A matrix with only one column is called a column matrix. So let us look at example B. B has one column, 1, 2, and if you notice they're running vertically. A matrix with only one row is called a row matrix. And in matrix A, we have 1 row, 3, 4, which runs horizontally.
Oh, so that means how we're standing to the viewers now, this would be a...
I think it's a row matrix.
Yes, it's a row. And if we wanted them to really have that visual representation of a column, how would we do it?
We would have to be one behind the other.
Right, one behind the other. That's good. We're also going to be looking at the dimensions of a matrix tells its size, the number of rows and columns of the matrix in that order. When working with dimensions of a matrix, always remember rows by column. For example, here we have in matrix A. So we have 3 and 1 will be a row, and 4 and 2 will be our second row. So 3 and 1 will be one row. 4 and 2 will be the second row. And then 3 and 4 will be one column. 1 and 2 will be the second column. So in all we have 2 rows and we have 2 columns. So this matrix will be called a 2 by 2 matrix.
All right, so some points to note when multiplying a scalar matrix, when adding matrices or subtracting matrices. So we have to ensure the matrices are compatible with each other. That is, they must have the same dimensions, rows and columns, as was stated before.
Right.
And we also, after that is done, we can then add or subtract corresponding elements.
That's good. That's very good. Very good job, Brittany. All right, so we are looking at scalar multiplication now. And in scalar multiplication, each entry in the matrix is multiplied by the given scalar. Now, thinking about it, Brittany, scalar. Any idea what scalar means or what a scalar is?
I'm going to be honest, no. I have no idea what a scalar is.
I remember something though. I remember when going to school, I've always been told scalar can be a quantity, which means it can have a value, a numerical value, or it can be a letter. So we're going to go into matrices now, looking at scalar multiplication to see what it entails. So let's look at this example.
Okay.
So given that A equal 10, 6, 3, 7, we're asked to find 3A.
What's 3A? What's that? What you mean?
Are you asking me or are you asking the viewers?
Well, I'm asking both of you guys. I'm asking you and our viewers.
Oh man, all right, let me tell you what I think 3A means. 3A to me now means A, so I have 1A plus another A plus another A.
Oh, all right. So you know, I got this. That is just 3 times A. That's another way of writing it, don't it?
You got it, Brittany. You got it. All right, so if that is what it means, then our scalar matrix here would be 3 times our matrix A, which would then give us 3
times 10,
6,
3, 7.
So if it means then that we're going to be multiplying our scalar by each element in our, so it's going to be 3 times 10, 3 times 6, 3 times 3, and 3 times 7. So what we actually did was multiply our scalar 3 by each element in our matrix, which would then give us 3 times 10 is 30, 3 times 3 is 9, 3 times 6 is 18, and 3 times 7 is 21. So let's check to see if we're correct. Ooh, yes, I am correct. All right.
All right, so before we get into this activity, I remember earlier on in the week, you guys looked at addition of matrix and we just looked at scalar multiplication. So we're going to put everything together in this activity. So let's look at this. A and B are two 2x2 matrix such that A is 1, 2, negative 4, 3, and B is 5, negative 1, 0, 3. We're asked to calculate 2A plus B. Now let's look at that. So we're asked to find 2A plus B. Remember, we just looked at scalar multiplication, so we know that 2A is the same as saying 2 multiplied by matrix A plus B.
Good.
So let's walk through it. So it's going to be 2 times our matrix A, which is
1,
1,
2,
2,
negative 4,
negative 4,
and 3.
3, plus B, which is our matrix
5,
5,
negative 1,
negative 1,
0,
0,
3.
3. So just as a reminder, we're multiplying 2 by every element in our matrix A. So it's going to be 2 times 1, 2 times 2, 2 times negative 4, 2 times 3. And then we're adding that to our matrix B. So let's do a little bit of simplification. 2 times 1 will give us 2, 2 times 2, 4, 2 times negative 4, negative 8, 2 times 3, 6, and we're adding corresponding elements in our matrix B. And that simply means that our first entry in row in matrix A is going to be added to the first entry in matrix B. So that's going to be 2 plus 5, 4 plus negative 1,
Negative 8
negative
plus
8
0.
plus 0, and 6 plus 3. So let's look at our results. So we're going to have 7, 3, negative 8, and 9. So our result is a new matrix 7, 3, negative 8, 9.
Good
So let's
job.
check this.
Let's check to see if Brittany is correct. So she would have had the correct answer for 2A, which is 2, negative 8, 4, 6. That is indeed correct. And the final response now would give us 7, 3, negative 8, and 9. That's correct, Brittany.
Awesome.
Good job. All right, so based on what we would have been doing so far, we are going to now be looking at determinant of a matrix.
All right, so the determinant of a matrix A is denoted by modulus A by det A. The determinant exists only for a square matrix.
Square matrix? How? What are square matrix? Or what are square matrices? Or what exactly is a square matrix?
No, I'm sure you've heard of a square before. You know squares, right? And you know the properties of a square.
I do remember. A square has 4 equal sides, so all the lengths are equal.
That is correct. So, if it is that all the lengths are equal, in this case, we're looking at a matrix. So, tell me how that can relate now to my square matrix. How you think it would relate?
Oh, so that means the square matrix has the same number of rows and columns. Am I correct?
Give me an elbow.
Ooh,
All right.
I got it.
So that is exactly what a square matrix is.
Well, how are we going to find the determinant of a square matrix now?
All right, so let's see. The difference between the product of the elements on our leading diagonal and the product of the elements on our non-leading diagonal. So first, we have to start off by establishing what is our leading diagonal and how we find our non-leading diagonal. So given any matrix,
So we have matrix A, 1, 1, A, 1, 2, A, 2, 1, A, 2, 2. Can you show us what do you mean by leading and non-leading?
all right, so with my red marker, I'm going to go ahead and circle my leading diagonal. So my leading diagonal would be A11 and A22.
All right.
My non-leading diagonal, I'm going to go ahead and take my blue marker and circle my non-leading diagonal, which is A12 and A21. Now, as was stated before, you find the determinant of the matrix by finding the difference of these two products. Now, what we mean by product again, Camille?
Multiply.
Good. So it means that here, to find the determinant of A, I need to find the product of A11 multiplied by A22, and then I will subtract the product of A12 multiplied by A21.
Which gives us what? I'm not seeing it so clearly. Can you just simplify it for me, please?
So it's simply A11, A22 minus A12, A21.
And guess what? She is indeed correct.
I think I deserve an elbow.
All right,
my elbow. All right,
elbow. Distance, Brittany, distance.
All right, social distance.
All right, good job. All right, so since as Brittany would have done that for us, we're going to try one on our own now. So we are going to try one on our own.
All right, so as you can see, we have a matrix E, and you're asked to find the determinant of this matrix. So matrix E is 8, 2, 12, 3, and you're asked to find the determinant, Camille.
All right, so if I'm asked to find the determinant, I'm going to do exactly what you did just now. So I'm going to have my leading diagonal here, which is 8 and 3. So my determinant of E is 8 times my 3. Take away the product of my non-leading diagonal, which is 2 times 12. So now I have determinant of E to give me 24, take away 24. So I am now left with 0. So my determinant is 0.
I wonder if all the determinants are going to be 0, you think?
I'm wondering the same thing, you know, but if this determinant is 0, is there a special name for this matrix, this type of matrix, since as the determinant is 0?
Yes.
There is.
Yes, there's a special name. I think you call these matrix singular matrix. Now, singular matrix have a determinant that is 0.
That's good, that's true. But
all of them going to have a determinant of 0?
I'm wondering the same thing. And are all matrices singular?
So let's take a look and find out. So here we have another matrix A. Matrix A has entries 3, 2, 2, negative 3. And we're asked to evaluate the determinant of this matrix. Now, as was asked before, I want to find out if the determinant of this matrix is going to be 0.
Go right ahead.
So let's look at it. Again, start off by highlighting our leading diagonal. So we need to know the elements on our leading diagonal, which we circled with red. So the determinant of A is going to be the product of these elements, which is 3 times negative 3, subtract the elements on our non-leading diagonal, which in this case is 2, 2. So we need to find the product of these elements. 2 times 2. So it's 3 times negative 3, which would give me negative 9. Subtract 4. So the determinant of this matrix is going to be negative 13. Now the determinant of our first matrix was what again?
0.
And the determinant of this matrix A is negative 13. So are the determinants of all matrices going to be 0?
No, but if it's not singular, then I wonder if it's plural.
Well, I don't think they call it plural. I think they call it non-singular matrix.
Oh, I see. I get it. So if it's not singular, it
is
must be
non-singular.
Non-singular. Okay, I get it now.
So another important part of matrices is the adjoint of the matrix. So here we need to look at how we find the adjoint of the matrix.
All right. So here, for instance, if we're given a matrix A, and we're told that matrix A has elements A,
B,
B, C, and D. What exactly are we supposed to do with the adjoint of the matrix?
Okay. So we have to interchange the positions of the elements on our leading diagonal. So in this case, it will be A, D.
Oh, so we're going back now to the leading diagonal. So the elements in the leading diagonal now. So we're now going to have the adjoint of matrix A. So the first ones we're writing, we're going to interchange our position. So where my A is now, I will have D. And where my D is now, I will have A. And then what next do we do?
And the next thing is we're going to multiply the elements on our non-leading diagonal by -1.
Oh, so these elements now will be multiplied by -1. So B times, so are we going to change their position as well? Are we going to interchange them just like what we did in the leading diagonal?
You're not paying attention. You know, I said leave them as is and multiply by -1.
Oh, so I just multiplying. All right.
Yes.
So it's B times -1 gives us -B, and C times -1 gives us -C. So our adjoint of this matrix is indeed D, -B, -C, and A. So guess what? You see, because you show off so much on me, your turn now to try one on your own. And I want to see you get it.
All right, guys. So hopefully I get this one right. So let's go. We have a matrix C.
C, which is 2, 9, -3, -4.
All right. So let's see. We said that we'd start off by looking at our leading diagonal. So I'm going to circle the elements in my leading diagonal, which in this case is 2, -4. And we said that we're going to interchange the positions of 2 and -4. So I'm going to switch positions. So it's going to be -4, where 2 was, I put -4, and where -4 was, I put 2. The second thing that we said is that we're going to multiply the elements on our non-leading diagonal by -1. Again, we're just multiplying by -1, nothing more. So it is 9 multiplied by -1, which would give me -9.
-9, yes.
And -3 multiplied by -1, which would simply give me 3.
+3, yes.
So the adjoint of matrix C is simply -4, -9, 3, and 2.
Good job, Brittany. Very good job. So far, you think they're getting it at home?
You know, I really hope they are. I really hope they are.
I hope they're following too, because this topic is a very fun topic. It's so exciting, so exciting. So we're now going into another aspect of matrices. We're now going to be looking at the inverse of a matrix.
Now, in order to find the inverse of a matrix, it must be square. Now, Camille, what did we say was a square matrix again?
Same number of rows and columns.
Pick up yourself. All right. So it must have the same number of rows and columns. The determinant cannot be 0. And the inverse of the matrix is denoted by A to the -1. So it's A to -1. Now, I'm sure you guys remember your indices, and we know that when we have any number raised to a negative index, it's the same as saying 1 divided by A.
Or any letter, seeing that we're looking at A right here. So it can be any letter or any number, anything whatsoever that is raised to the power of -1 will give us 1 divided by that letter, number, or whatever it is. That's correct, Brittany.
That is correct.
And the inverse of a matrix is equal to 1 divided by the determinant times the adjoint of the matrix. So my question now, if I have a determinant which gives me 0, what does that mean about my inverse? Because my determinant is, so let me write it. So my determinant, it's 1 divided by my determinant multiplied by the adjoint of the matrix, right?
Yes.
So what if I have a determinant Like the first one, remember when we found the first one and you told me it was a singular matrix and the determinant was 0?
I remember.
So what we're going to do now, because it's 1 divided by 0?
Well, I know that 1 divided by 0 would give me 0. And any number multiplied by 0 is 0. So there, if my determinant is 0, it means I can't have an inverse, don't it?
That means not all matrices or not all matrix has an inverse then based on what you just said, you know?
Exactly.
You know, come to think of it, that's true. Not all matrices have an inverse. They must have a determinant which is not 0. As long as it's not 0, they'll have an inverse, all right?
There we go.
So here we're going to be looking at some CSEC questions. And the first one that we have here, we're going to be working it together. But guys, we're asking you at home to please try while we are helping as well. So we are told that M equal
2, 5, 7, 15. And we're asked to show that M is a non-singular matrix. Now right there, non-singular, keyword. What does that mean?
That my determinant cannot be 0. So that means I must have a determinant that is not 0. So I know how to work this, and I'm remembering what you just done saying, man. So I'm remembering. So you are saying now that my determinant, this would have been my leading diagonal, and I'm multiplying my elements in my leading diagonal first. So let me write it. So the determinant of M gives me 2 times 15 take away 5, the product of 5 and 7. So here I would have 30 take away 35, which I am now left with negative 5. So my determinant of B is negative 5.
All right.
Was I correct? Was I correct? Can we see if I'm correct?
No. Let's wait.
I want to know if I'm correct because
Right,
guess what?
fine.
You're doing the inverse part of it, you know? You're doing the inverse part, so let's see if I'm correct.
All right, go ahead.
Ooh, elbow. I'm correct. So your turn now to show us the inverse of matrix M.
All right, so when we talk about the inverse of a matrix, there are 2 things that we need to know. We need to know the determinant, which you just found, Camille, and we also need to know the adjoint of the matrix. So let's start off by writing the adjoint of matrix M. So the adjoint of M. Now, as we remember, we're going to focus first on our leading diagonal. So the elements on our leading diagonal need to be interchanged. So that means we start off with where 15 was, where 2 was, we place 15, and where 15 was, we're going to put 2. The second thing that we need to do is multiply the elements on our non-leading diagonal by negative 1. So that's 5 multiplied by negative 1, which will give us negative 5. 7 multiplied by negative 1, which will give us negative 7. So there we go. I've just written down the adjoint of matrix M. But am I going to stop there?
Not at all, because we're asked to find the inverse.
So let's go ahead and find the inverse of this matrix by putting it all together. So the inverse, or M, negative 1, raised to the power of negative 1, is equal to 1 over the determinant of M multiplied by the adjoint of M. So this is simply going to be the determinant that we found in part 1, which is negative 5. So it is 1 divided by negative 5 multiplied by my adjoint matrix. 15, negative 5, negative 7, 2. Now remember when we started off, we stated that when multiplying a matrix by a scalar, every single element in this matrix must be multiplied by my scalar. So let's go. It's going to be 15 multiplied by negative 1/5. So it's going to be 15 divided by negative 5. It's going to be 5 multiplied by negative 1/5, which is going to be is going to be 5 divided by negative 5.
Negative 5.
We're then going to multiply negative 7 by negative 1/5, which is just simply negative 7 divided by negative 5. 2 multiplied by negative 1/5, which is 2 divided by negative 5. Now let's try to simplify here. We have 15 divided by negative 5, which is just simply negative 3.
Yes.
We have negative 5 divided by negative 5, which is just simply 1.
Positive 1.
We have negative 7 divided by negative 5, which is 7 divided by 5. We have 2 divided by negative 5, which is negative 2/5. So my inverse, the inverse of m is simply negative 3, 1, 7 divided by 5, negative 2 divided by 5.
That's good. That's good. That's good, Brittany. Let's see if Brittany is correct as well. Yes, she is indeed correct. But there's one thing that I want us all to remember. And in remembering all this, I want us to know too that everything that we would have been doing from we started this morning, we have to ensure that we are doing it now, or we have done it. So if you look at here, we would have had our scalar multiplication taking place. Now before, we would have found our determinant, which we did earlier. So everything in math relates, it's related. So every single thing, yeah man, that's why maths is so nice, you know, maths is just fun. You just have to make it fun. Everything we did, you realize we would have done it earlier. So now it's your turn, and we want you to try this one at home. So you're going to try this one at home for us. We're going to be helping you too, but we're giving you some time to try this one on your own as well. So the matrix T is such that T equal 2, negative 1, 1, and 3. What are we asked to find again, Brittany?
So it seems that we're asked to find the inverse of T.
Oh, so if we're finding the inverse of T, do we need to do anything special? We can just write down an inverse?
Lord, I think we need to do so many things. We have to find determinant, we have to find adjoint, and then we have to put all of those things together to find the inverse.
Because all things work together for matrices, right?
Amen, amen. No,
elbow.
Elbow.
Right. Good, so we're going to try this one now.
So T is 2, negative 1.
2, negative 1.
1, 3.
1, 3.
And we're going to find the inverse. So what we're going to start off with?
Our determinant.
All right, let's go.
So remember, we don't only have to write the determinant of T like that. Let's write it a different way so you can be exposed to both ways. So you can also write the modulus of T to have given us now the product of the elements in our leading diagonal, which is 2 times 3 minus the product of the elements in our non-leading diagonal. So we are now left with 6 minus negative 1, which gives us 6 plus 1. So we are left with 7. So our determinant for T is 7. So now we are asked to look at the adjoint. So our adjoint now.
You want help?
Yeah, man, enough help.
All right, so with the adjoint, we have to interchange the elements on our leading diagonal. So where 2 is, I'm going to put 3, and where 3 is, I'll put 2. So it is going to be 3, 2. Then we're going to multiply the elements on our non-leading diagonal by negative 1, which is 1, negative 1.
Right.
So the adjoint of this matrix is 3, 1, negative 1, 2.
Good.
You can take it from here?
No, man.
What do you mean?
Continue. You're doing such a good job. Continue.
Lord. All right. So now we need to find the inverse of this matrix by putting everything together.
Everything.
So T inverse is simply going to be 1 over the determinant of T multiplied by the adjoint of T. So let's go. The determinant of T was what again? It was
7.
7. And the adjoint is going to be 3, 1, negative 1,
2.
Remember, scalar multiplication. every element in my adjoint matrix must be multiplied by 1/7. So it's simply, and I'm going to write it out for you guys this time. It's going to be 1/7 times 3, 1/7 times 1, 1/7 times -1, 1/7 times 2. So this is going to give me 3/7, 1/7, 1/7 times -1, -1/7, 1/7 times 2, 2/7. So T inverse, bam. Am I right?
You are so right.
You sure?
I'm very right. You are so right. Good job. So right here, the first thing we would have evaluated was our determinant of T, and then we would have looked at our adjoint of T, and then now we would have put everybody together to have our inverse of T. I wonder if they got it right at home. You think they're following us?
Guys, tell me that you're following us at home. I really hope that you're
We
following.
want you to be following, okay? We need you to be following, because you realize that we have been taking it step by step in order for you to follow. All right, guys? Now, so far, we're going to be doing a little recap shortly, but so far we have been looking at our determinant, or scalar multiplication, or adjoint of the matrix, or inverse of a matrix. And you know, honestly speaking, Brittany, I told you when we just started, you know, I really love matrices, because if you look on it, if I do one thing and if I remember what my leading diagonal is, and then I remember what my non-leading diagonal is, I'm going to use the same thing from my determinant with leading and non-leading to get my adjoint. I'm going to be getting that, you know, so it can help.
Math's nice.
Math's sweet. No, you know, nice. It's sweet.
Math's
It's sweet,
sweet.
bad. It's sweet, may I tell you. Sweet, man. So we're just going to be doing a little summary of what we would have done so far.
All right, so as we stated before, we started off with the determinant. We looked at the determinant of the matrix, which is denoted by modulus A or det A. We also looked at what the determinant of a matrix is, which is simply the difference between the product of the elements on our leading diagonal and the product of the elements on our non-leading diagonal. A matrix is singular if it has a determinant of 0.
So that means what then, Brittany? If the determinant is not 0. What we said it was again? No, it's
you
not
didn't call
plural,
it the plural
man. It's not
matrix, you
plural.
remember? No,
Yes, it's not
but
that,
it is
man.
a non-singular matrix.
Yes, you're right.
So it's a non-singular matrix.
So that means our matrix can be either singular or non-singular matrix.
And let us make sure that people at home are following. If the matrix has a determinant of 0, then that matrix is singular. If the matrix has a determinant that is not 0, then the matrix is non-singular.
That's right. That's right. And then now we also looked at adjoint of a matrix. So with the adjoint of a matrix now, we interchange the positions of the elements in the leading diagonal and multiply the elements in the non-leading diagonal by -1 while keeping them in their positions, which means they're not going to move, they're going to stay one place. All we're doing to the elements in the non-leading diagonal, we're just multiplying them by -1. And finally, the inverse of a matrix is 1 divided by the determinant times the adjoint of the matrix. Remember now, if the determinant is 0, there is no inverse for that matrix. We have to remember that. Anything else you want to share with them before we go, Brittany?
All right, let's check off the list. We'll talk about the determinant.
Yes, we spoke about the determinant.
We spoke about the adjoint.
Yes, we spoke about the adjoint.
Oh, the singular thing go again?
The singular, man. With the singular now, singular matrix, the determinant is 0. So the determinant of a matrix, if it is 0, then it's called a singular matrix.
All right, if it is non-singular, what happened to the determinant?
The determinant is not 0. It won't be 0.
Okay, and we looked at how we put everything together to find the inverse of the matrix. How we did that again?
Well, we first would have to find our determinant of the matrix, ensuring that it's not 0 before we can move on any further. And then now we look at the adjoint of the matrix. After we look at the adjoint of the matrix, we put both together. So the inverse now would be 1 divided by our determinant multiplied by the adjoint of that matrix to give us our inverse. And remember too, in doing the inverse of a matrix, we are looking at scalar multiplication, because you have to multiply the scalar by each element in the matrix. All right, guys?
So excellent, Camille. Guys, I really hope that you are following with us at home, and I hope that this was easy for you to get, right?
I hope so too. I really hope so too.